So the first slide, I'm going to start with component form for a vector. Okay, we would like all vectors to be in component form. And if you'll remember back in chapter 6, when we first started talking about vectors, we said vectors are basically like directed line segments. They have magnitude and they have direction to them. Because they have magnitude or some length, they have some like start and end point, so an initial and a terminal value. If we wanted to change it into component form, we would take like the horizontal components and we would do terminal minus initial to get v sub 1, and then we would take the vertical components of the initial and terminal point, terminal minus initial to get v sub 2. So you always do the end point minus the start point to get it into component form. Well, in 3 dimensions, instead of just having a horizontal and a vertical component, we have a third dimension, right? And that's really represented, we use our x to represent like our forward and backward axis. So we're just going to add an extra component. So in 3 dimensions, component form looks like v sub 1, v sub 2, v sub 3. And those correspond just the same directions that we would use for ordered triples. So v sub 1 is really like our x, which moves forward and backward in the 3-dimensional coordinate system. V sub 2 is our y, which moves left and right in the 3-dimensional coordinate system. And v sub 3 is like z, which moves up and down. We also talked about something called standard unit vector notation. And it was a linear combination of the horizontal and the vertical components, so v sub 1i plus v sub 2j. And this piece comes from the standard unit vectors, I and j, where I was just the horizontal component is moving, so you have a unit of 1 in the horizontal component. There is no vertical component. It is 0. Okay. And then j was the vector that just moved up. Okay. So 0, 1. Those are our standard unit vectors. Spell that right. And so if you take like your horizontal component as a scalar to the standard unit vector I, or the horizontal standard unit vector, then you just are going to come up with component form. Okay. But these are just talking in terms of the 2 standard unit vectors. And so in 3 dimensions, we're just going to have a third one. Okay. So the standard unit vector notation is going to look something like this. V sub 1i plus v sub 2j plus v sub 3k. The standard unit vectors, of course, have to change a little bit because now we're working in 3 dimensions. So I is really like 1, 0, 0. J is 0, 1, 0, and k is 0, 0, 1. So it's just breaking them up into like their individual sort of like components in the direction that they would go. We also talked about last chapter magnitude. So magnitude is the square root of v sub 1 squared plus v sub 2 squared, your horizontal component squared plus your vertical component squared. And when we introduced that magnitude, we kind of looked at it in terms of trigonometry, right triangle trig, so we saw it as a right triangle and did Pythagorean theorem. We also know that Pythagorean theorem really is the distance formula, so that's just another version of the distance formula, okay, a triangle formed at the point v sub 1, v sub 2, and then 0, 0 in the x-axis. So we know already from our notes on Tuesday, if this is like the distance formula in 2 dimensions, then we would just apply the third dimension to the distance formula. So we're just going to do a plus v sub 3 squared. And so our magnitude, and remember the abbreviation for magnitude are those double bars if you want to add that in there. Our magnitude is the square root of v sub 1 squared plus v sub 2 squared plus v sub 3 squared. So as you're looking at, like, what are we changing, most of the time we're just adding an extra thing, okay, for that third dimension. Unit vectors were another topic that we discussed back in chapter 6. A unit vector is special because it has a magnitude of 1 unit. Not all vectors have length of 1. Okay? Unit vectors do. So we would say, like, well, how could we get a vector going in the same direction as another vector, but instead of having like its own magnitude, how could it have a magnitude of 1? Well, if its magnitude was the square root of 29, to make that equal to 1, we'd just divide by the square root of 29. So that's what you see right here. Take your vector, both components, and divide by its magnitude. So we're going to do the same thing if we want a unit vector in 3 dimensions. Take all 3 components, v sub 1, v sub 2, v sub 3, and divide by your magnitude. When you're calculating magnitude, you'd be using the 3-dimensional magnitude as opposed to the 2-dimensional magnitude. And the last thing that we will kind of review right here are how we calculated dot products. So dot products, if you have some vector u with components u sub 1, u sub 2, and a vector v with components v sub 1, v sub 2, you multiply your horizontal components and add with the product of your vertical components. You could imagine in 3 dimensions, we have an extra component, right? We'd have a u sub 3 and a v sub 3. So we just need to add that product. So our new dot product in 3 dimensions is u sub 1, v sub 1, plus u sub 2, v sub 2, plus u sub 3, v sub 3. So it's been a while since we did chapter 6, since we talked about vectors, and we'll go through eventually some examples, kind of refresh our memory, okay, how would we do this? But remember, when we did do vectors, it's very simple work for the most part. Okay, it's not really difficult math, it's just remembering what all of that stuff means. Does anybody have any questions that's on the screen right now before we leave this? Okay. The next slide, I don't think you have to write anything down. Okay, I just want to make you aware of this is available on page 781. It talks about vector operations, some of which we have already covered on that previous slide, and then some very basic that I don't think we really need to write anything down for. So one thing that I didn't really feel like we needed to write down in chapter 11 was the first statement, 2 vectors are equal if their corresponding components are equal. Okay, that makes sense to all of us, I think. The horizontals have to match, the verticals have to match, and then in 3 dimensions, we'd have that forward and backward piece. Okay, would have to match. We already talked about magnitude, so you can see they're just adding that extra component. We already talked about a unit vector, so that's still there. 4 and 5 are 2 that, again, I don't think we need to write anything down. I feel like you guys will be totally okay with this. If you want to add 2 vectors, add the horizontal, vertical, forward, backward components with each other. Okay. If you're doing a scalar multiplication for a vector, you have to distribute the scalar to all components. Okay. So again, I don't think we have to write anything down there. And then they also have the dot product. So if you want to check for vector operations or you need to review the rules or the properties, that's available to you on page 781. Here's an example. Find the component form and the magnitude of the vector v that has initial point 241 and terminal point 352. When you get that written down, start thinking about what are you going to do with the terminal and the initial points so that you can get component form. Have a discussion at your table. Like, what do you remember doing back in chapter 6? You've got an initial point, you've got a terminal point. How can you get your component form? What do we do to get component form?
Initial point from the terminal point.
Initial point from the terminal point. So which one do you have to do first, or put the number in first? Terminal, right? It has to be terminal minus initial. So maybe make a note in your notes if you need to remember that. If you do it the opposite direction, you'll have a vector going in the wrong direction. Okay, so I'm going to show my work because this is my notes, of course. And I'm going to go from the terminal to the initial. So I'm going to do 3 minus 2, 5 minus 4, 2 minus 1, which leaves me with 1, 1, 1 for my component form. What else does that question ask you to do? Find the magnitude. Okay, so calculate the magnitude from your component form. This one's very easy, right? The square root of 1 squared plus 1 squared plus 1 squared, which is just the square root of 3. Okay, so that's not bad. Okay, so get component form, then do magnitude. You could do that. Can you find a unit vector in the same direction as vector v? So look back if you copied anything from that first slide we went over. What do you do for a unit vector? This vector v is not a unit vector right now because its magnitude is square root of 3, which is not 1 unit. So how are you going to get it to have a magnitude of 1 unit? What should we do to find the unit vector? Divide by radical 3. So take your unit, or take your vector, 1, 1, 1, and divide by radical 3. You're going to divide each component individually by radical 3. I'm going to go ahead and divide and rationalize my denominator right away. So then my unit vector is square root 3 over 3, square root 3 over 3, square root 3 over 3. This is my unit vector. If I were to do the magnitude for the unit vector, it should come out to equal 1. Okay, so you could think about if you did the square root of 3 over 3 squared plus the square root of 3 over 3 squared plus the square root of 3 over 3 squared. Each of those are going to come out to be 1/3. So 1/3 plus 1/3 plus 1/3 is 1. And then the square root of 1 is 1. So it is a unit vector. Okay. You don't usually have to check it, but that's just what that means. Are we okay with this? Jogging your memory from chapter 6? Okay, let's try some other things. Find the dot product for me if you would. Dot product for -135 and 0, 4, -2. check around with the people at your tables if you're agreeing with your dot product once you have one. I'm gonna, of course, again, show my work because these are my notes, so I always think that's a good idea. So if you're ever looking back, you remember how you got it. 0 plus 12 plus negative 10, so our dot product is 2. Excellent. Just as a reminder, and you can jot this down in your notebook if you like, if the dot product were to equal 0, it would also tell us that our vectors are orthogonal. Do you remember what orthogonal means? Perpendicular. So it would mean that the vectors form a right angle. Okay. And so we could certainly take two vectors in space and have them form a right angle. That seems like something that's very possible. So that carries over. If the dot product is 0, then your vectors are orthogonal, which means perpendicular. Creates a 90-degree angle. Okay. Let's see, speaking of angles, I think our next slide is going to be the angle between two vectors. Do you remember this formula? Cosine theta is equal to the dot product of u and v divided by the product of the magnitudes for u and v. If you want to add some things into your notes to help you, u times v is really the dot product. So you're going to put the dot product in the numerator. And then down here we're talking about the product of the magnitudes. So you'll have to have a magnitude for u and a magnitude for v. Don't forget over here, you'll have to use inverse cosine to solve for theta. So there's like the piece on the right, you got to do that work. You got to fill in the dot product and fill in the product of the magnitudes. But when you get that ratio, you also have to take the inverse cosine of that ratio to actually find your angle. And when we did this back in chapter 6, the angle, the decimal angle, probably makes more sense to us in degrees than it does in radians. So if you want to pull your calculator out right now and make sure it's set to degrees, okay, that would be acceptable. And we'll find the angle between these two vectors. 4, negative 1, 3, and 0, 1, 5. So on this particular type of problem, I prefer to kind of work out my 3 pieces and then plug them into the formula as opposed to trying to write it all out in the formula from the beginning. So off to the side here, I'm just going to calculate my dot product and my 2 magnitudes. So my dot product of u and v would be 4 times 0 plus negative 1 times 1 plus 3 times 5. Which is 14. And then I would do the magnitude of u, the square root of 4 squared plus negative 1 squared plus 3 squared. That's the square root of 26. And the magnitude of v is the square root of 0 squared plus 1 squared plus 5 squared, which is also the square root of 26. These magnitudes won't always come out to be the same. They just happen to be the same in this problem. Am I doing everything okay? Or do you have a question? I just wanted to make sure that I'm not making a mistake. You would tell me if I was making a mistake? Okay. Now I'm going to plug these things in. So I want to do the cosine of theta is equal to 14 over the square root of 26 times the square root of 26. Now, on that one works out really nicely. I could just write 26 in the denominator. The square root times the square root, so you cancel out. But if I was just going to leave it as like the square root of 26 times the square root of 26, if I type that into my calculator and I don't have math print, remember in the denominator that product would need to be in a group of parentheses. Okay, so go ahead and type this into your calculator. Make sure that your calculator is fully functioning for trig and division and multiplication. I believe you should get as a final answer 57.4. Pull out my calculator and double check. Okay, so type it in and make sure that your calculator works. Yep. If you just do the right side, it's like 0.53846 stuff. And you have to inverse cosine that. Anybody having trouble getting 57.4? Okay. Then we have a couple other things to talk about. One of them is parallel vectors. Okay, and I'm not certain that we did this back in chapter 6, so this is definitely something that you would want to write down in your notes. Okay. How can you check to see if vectors are parallel? Check to see if there is some scalar that connects them. Okay, so two vectors, vectors u and v, are parallel if there is some scalar c such that u is equal to c times v. It does not matter which way you write that. U is equal to c times v, v is equal to c times u. There's a scalar both ways. Like if I'm going to double something, then my scalar is 2, but in the other direction I'd be halving it. So then my scalar would be 1/2. But either way, there's a scalar. Okay, so it doesn't matter which order it goes in. You never have to worry about what's u and what's v. Here's an example that will work out to kind of give you an idea of how this works. Vector W has an initial point at 2, -2, 1, and a terminal point at 0, 4, -3. Which of the following is parallel to W? And I have a list of 3 vectors. So let's brainstorm. What kind of tasks would we be doing so that we could check to see if these are parallel?
Indicate each component of the vectors and divide them by the same component in the one that you're given, and you get the same number from all 3 components of their area.
Okay, so then what do I use for vector W?
You have the component formula there.
Okay, I think that's where we should start, right? We have a terminal and an initial point, we should have the component form for W. So first thing you can do, whenever you're given an initial point and terminal point, is get component form. So let's find W. W would be 0 - 2, so -2, 4 minus negative 2, so positive 6, and negative 3 minus 1 is negative 4. Okay, so now I have a component form for W. And Jacob, can you describe to us, now that we have this component form, what do you want us to do with W?
We do like a guess and check method where you take W and divide it by one of the other vectors, and each component should give you the same number of parallel.
Okay, so you want to divide the components of W with the components of the other vectors to see if they all have the same scalar. So like, we would take the horizontal component, negative 2 divided by negative 1, 2. 6 divided by 3, 2. Negative 4 divided by negative 2, 2. Is there a scalar there? Yeah. So we could say that W is really equal to 2 times U. So this is one of my parallel vectors. We could do the same check for V. Negative 2 divided by negative 2 is 1. 6 divided by 6 is 1. Negative 4 divided by negative 5, 0.8. Not parallel. And we could check the same way. Negative 2 divided by 3, negative 2/3. 6 divided by negative 9, negative 2/3. Negative 4 divided by 6, negative 2/3. So we could say that W is equal to negative 2/3 times U. This is another parallel vector. So that's a really efficient method for checking to see if they have a common scalar.
I'm sorry, I want to times V.
Oh yeah, sorry. Thank you, Catherine. I agree. I know you guys would yell at me if I did something wrong. Can always count on you. I appreciate that. Yeah, it would be negative 2/3 times Z. Okay. Now, some of you might have been able to see like, oh yeah, I'm just multiplying all of U by 2. So maybe you didn't have to do that check for everything, but I like Jacob's method. It'll work. Okay, so if you're having trouble, just divide every component and see if they're the same. Any questions there? Okay, one last thing. Collinear points in space. The points P, Q, and R are collinear, meaning they all lie on the same line, if the vectors PQ and PR are parallel. One thing that I could say about this statement to kind of help you as you're preparing for that chapter 11 test you'll be taking next Wednesday is pay attention to the two vectors that you're checking. The vector that you check to see if they're parallel, they should have the same initial point. So if you think about it geometrically, you're checking to see if things lie on the same line. You're checking like you have initial point P and it goes through Q. Okay, that's like a ray. Could you also have initial point P that goes through R, and then they're all on the same line? So that's kind of what you're checking. Initial point has to be the same. Here would be an example. Okay, so I've got 3 points that are out in space. I've got X, Y, Z. So 1, negative 1, negative 3, 0, 4, negative 2, and 6, 13, negative 5. And I would just want to find the two vectors. It wouldn't really matter which vector you chose, okay, like if they were labeled differently, as long as they have the same initial point. Okay, so I'm going to do PR and PQ. For PR, I have to go to R first and subtract corresponding components. So 6 minus 1 is 5, 13 minus negative 1 is 14, and negative 5 minus negative 3 is negative 2. So I get that component form for vector PR. And then I do the same thing for vector PQ. Terminal point is Q, so start with Q's components, subtract P's. 0 minus 1 is -1, 4 minus -1 is 5, and -2 minus -3 is 1. Is there a common scalar like we just checked for? So thinking about Jacob's method, 5 divided by -1, is that the same as 14 divided by 5? So these are not collinear. There is no common scalar. I'm just going to say no scalar. Okay. So you find the component form for the two vectors with the same initial point and just check for a scalar. Okay. You'll have homework assignment tonight. Okay. It is 7 through 13 odds and 19 through 59 odds. Of course, initially that seems like a lot, but you're only doing the odd problems, and they're vectors, so some of it is going to go by very quickly. So we have just about 10 minutes. I'd like everybody get a textbook out and get started. If you've been leaving your textbook in the room, they're over on the shelf.